Hi, I'm Sarah. I'm one of the authors of this study where we present a high-resolution climate database for Africa. While simple interpolation models can predict some climate variables such as temperature, where you have linear relationships, for instance, if you have latitude, longitude, and elevation, you can pretty much accurately predict the temperature variable. However, this is not the case for some complex climate variables, for instance, precipitation. In mountainous areas, there is orographic lift that leads to precipitation on the windward side of the mountain, but there is no precipitation on the leeward side of the mountain because the air there is dry. And simple models are not able to predict this. However, with deep neural networks, we see that these patterns, complex patterns, are achieved. As you can see, on this side, we have high precipitation on the windward side of the mountain and little to no rainfall on the other side. And that brings us to our three-step methodology where we have deep neural networks at their center. In step one, we use thin plate spline interpolation, traditional interpolation methods to produce the first set of climate grids. We then feed these climate grids into the deep neural networks along with topographic and monthly wind variables to produce fine-tuned grids. And this is all done at a coarse resolution of about 2.5 arc minutes, which is about 4 kilometers. And at this point, we also perform an independent checkerboard validation to assess the performance of the deep neural network. So these fine-tuned grids are then treated to a lapse rate based downscaling, and also bioclimatic variables are calculated and derived to produce the final grids, and these grids are even at a final resolution of about 30 arc seconds. Here I present some examples of our input variables, including compound topographic index and topographic position index, and also the windward distance to coast, leeward slope exposure, and these reflect the atmospheric influences on climate, such as winds. So this is the architecture of our neural network. We have a wide to narrow architecture whereby we start with a high density of nodes at the start to capture the wide variety of interactions across the continent. An example of a climate grid produced. So this is January precipitation, and we can see the model accurately predicts the high precipitation in the windward side slopes and low precipitation on the leeward side slopes. And to see how it improves the thin plate spline, you can see it. The blue represents increasing precipitation modeled by the thin plate spline, and it decreases that on the leeward side. To validate our model, we use the checkerboard validation method, and here we retain stations in the white checkers to run the model and use the stations in the black or gray checkers to validate. The other validation that we did for this study was a visual validation where we compared our neural network to a Google satellite image of vegetation, and we can see areas with high precipitation coincide with the areas with high vegetation. We produce this data in multiple time periods, from 30-year normal periods to monthly data and even future projections. It's available with multiple variables, monthly, seasonal, among others. In the end, there's a large number of high-resolution grids. So for the end user, this can all be queried in a very user-friendly ClimateAF software. Now I'm going to show you briefly how the software works. Once you download the software, it will come in a zipped folder that you unzip in your desired location. It will have these 3 folders and the software. This is the .exe, and double click it to open. So for a single location query, you just need the latitude, longitude, and elevation, and then select the variable. So we want the normal 61 to 90, and then start. You'll have all these variables. If you want a different, say you want any data, you want 1901 data in 1902, start. So if you want future data, future periods, say you want 8 GCM ensemble for 2011-2040s, start. So right now we have 25.5 MAT, and this changes to 26.4 MAT. So that's how you use the single query function. But you can also have multiple locations which you can query at the same time using an input file. So I have this already made example set of coordinates for location in Uganda. So I already have the ID1, ID2, latitude, longitude, and elevation, and these are the standard required fields for this software, so you must have them. And so let's save our coordinates. Save as, go to my current folder. So I'm just going to save these as a CSV and save. Yes. And then close. I don't have to save it again. So I have my CSV file right here. I'll go back to my software, select input file. It's the only file that shows up. Coordinate CSV, open, select again. I want the normal periods, and I want all the variables. Select input files. I already uploaded that. Specify output file. I have to give it a name, so I'm just going to call it coordinates output or all variables, and save, and then click start. 5 entries completed. So right here we see the software has saved my new variables with my coordinates with all the climate variables that I require, and that's how you use ClimateAF software. The software is freely available for download at that link. If you run into any issues, you have any questions, any feedback, send me an email, or Andreas Haman, who is the corresponding author. This is the link to our publication. Thank you for listening. Yeah, thank you.